Lesson 11.1.2 Linear Functions. Jean lives in a housing cooperative where she shares food and housing expenses with several roommates. Jean needs to buy meat for her housing cooperative. She has two options. She can go to a Fresh Plus store and pay $4.50 per pound, or she can go to a warehouse store like Costco or Sam's Club and pay $3 per pound. Fresh Plus is near her housing cooperative. A trip to Fresh Plus would cost 50 cents for gas. The warehouse store is further away. A trip to the warehouse store will cost $5 for gas. Our goal is to write a mathematical function or formula where this mathematical function is for the amount of money that Jean would spend at each of the stores. To do this, let's think about the patterns in total cost for each of the two stores. To help us observe those patterns, we can make a table of costs. In this table, define X and Y as the following variables. X is the number of pounds of meat purchased, and Y is the cost of purchasing the meat at Fresh Plus. The table below allows X to vary from 1 to 5 pounds. So number 1, complete the remaining two calculations in the table. Fill in the value in the Fresh Plus cost column. And what I want us to do while we're filling this out is think about the patterns that we notice. So let's take a look at this table. We see that we have X as the first column, and then the middle column is Y, which is our computation, and then the last column is the Fresh Plus cost column. So then moving down to the second row, we have X is equal to 1. So this is saying, what if she bought 1 pound of meat at Fresh Plus? So if she were to do that, she first has to go to Fresh Plus. She has to make that trip, and that trip is 50 cents for gas. And then she has to buy the 1 pound of meat. And if she does that, it's $4.50 per pound. So the 50 cents, which is 0.5, plus $4.50 for the 1 pound of meat, that gives us a total cost of $5. So if she drove to the Fresh Plus store, bought 1 pound of meat, and came home, that would cost her a grand total of $5. So now what if X is equal to 2? This is in the third row. If X is equal to 2, then she's buying 2 pounds of meat, so she still has to drive to the store. That's still going to cost 50 cents, but then she's going to add to that cost 2 pounds times $4.50. So that's $9 plus 50 cents gives her a total cost of $9.50 in the last column. What if she bought 3 pounds? Well, it's still the same price to go to the store. So now let's start to recognize the pattern that we see. She still has to pay 50 cents if she's going to the store. So we start with that, 0.5, and then we add how many pounds of meat did she buy? 3 times the $4.50 that it costs per pound. So if you multiply, remember your order of operations, 3 times $4.50 first, and then add 50 cents, you're going to end up with $14 as we have in the last column. So now if she goes to the store and buys 4 pounds of meat for the second to last row, Y, the computation would be 0.5 for the cost of the trip plus 4 pounds times $4.50 per pound. So again, use your order of operations. 4 times $4.50, that's $18. Then add the 50 cents, that's a total of $18.50. And then finally, for 5 pounds of meat, again, the same pattern that we've established before. She has to spend $0.5 or 50 cents for the trip. And then we need to also add 5 pounds times $5.50. Oh, not $5.50, $4.50. So then 5 times $4.50, and then add another 50 cents for the trip, and you end up with $23. All right, so that gives us a sense of what her costs would be for varying amounts of meat from this one store. Now let's look at number 2. Look at the pattern in the formula. How does the cost change each time Jean buys 1 more pound? So if we notice in the middle column, that's where our formula was, our computation. We saw that she always had to pay 50 cents to go, but the thing that changed was how many pounds of meat she was buying. We can also take a look at, in the last column, how does the cost change each time? How did the cost change when she went from 1 pound to 2 pounds? Or when she went from 2 pounds to 3 pounds? Or from 3 pounds to 4, or 4 pounds to 5? Can you recognize the pattern there? How much did it increase from $5 up to $9.50? That was an additional $4.50 because she bought an additional pound of meat, which costs $4.50 more. Then when she went from buying 2 pounds to 3 pounds, that was another $4.50 that was increased. So how does the cost increase each time Jean buys 1 more pound? It increases by $4.50. All right, so now we just recognize some patterns from that one option. So now number 3. Imagine now that X pounds of meat are purchased from Fresh Plus. If we don't know the value of X, we can still represent the cost Y with a formula, a mathematical function. Look at the Y computations in the table that we had above. Use these computations to determine the formula for the cost of X pounds of meat. The way to imagine how to do this, just take a look at what you've already done. Like when you did X is equal to 4, where did the 4 go? It was being multiplied by the 450. When you did X equal to 5, where did the 5 go? It was also being multiplied by the $4.50. So whatever X is, it's going to be multiplied by $4.50. So X times $4.50. And what did you do after you did the multiplication? By the order of operations, you then had to add the 50 cents. That was the 0.5. So all we've really recognized is that these numbers are just placeholders for X. They're just specific numbers. X is the thing that is varying between 1 and 5. It's the variable. So really all we have here is just, instead of writing those numbers, it's just an X times $4.50. Another way that you could write this, Y is equal to 0.5 plus 4.50x. That's usually how you see these sort of formulas written. That's in fact something that you saw in Module 3 in Math 21A. So now number 4, let X continue to be pounds of meat purchased, but now let's define Y as the cost for the warehouse store. So now we're going to imagine that she goes to Costco or Sam's Club. Make a table like the one above. Write an equation for Y equal cost of buying X pounds of meat from the warehouse store. So let's start this just like we did on the previous one. Let's first think, well, how much does it cost to go to this warehouse store? On the previous page, it costs $5 for the trip. So I'm going to start by considering that. She'll always have to pay that when she's driving to Costco. And then we need to add, how much is it per pound at Costco? $3 per pound. So how many pounds is she buying in this first row? X is equal to 1, so 1 times $3. So what's the total cost for just 1 pound of meat? It's the $5 for the trip, plus the $3 for the 1 pound of meat. 5 plus 3 is $8. So now what if she buys 2 pounds? Y is equal to, still has to pay $5 for the trip, but now it's 2 for 2 pounds times 3 for the amount of money per pound. That becomes 5 plus 6, and that's $11. And then how about for x equal to 3? Now it's still $5 for the trip plus 3 pounds times the $3 per pound. This becomes 5 plus 3 times 3. That's 5 plus 9, which is 14. Do we also start to notice the same sort of pattern like we saw before? How much is the cost increasing every time she increases the amount of meat by 1 pound? Started at $8, then it increased by 3. Became $11. Then it increased by 3 again. Became $14. So what do you think the next cost is going to be? And the cost after that? Keep in mind that pattern, but also how the computation pattern is still holding too. 5 for how much it costs to go to the store, plus the number of pounds of meat, 4 times how much per pound, which is $3 per pound. So for 4 pounds, this becomes 5 plus 12, which is 17. And then for 5 pounds, it's 5 plus 5 times 3, which becomes 20. So what would you write for a formula this time around? Y is equal to 5 plus, notice the thing that was changing, that was varying, was the first part of the product. So that's the variable x. And then we multiplied that by 3. And a more familiar way for us to write it would be y is equal to 5 plus 3x. So now number 5, write the equations for the Fresh Plus and warehouse store costs. So I'm just going to organize those equations. So from Fresh Plus, that was y equal 0.5 plus 4.50x. And then for the warehouse cost, that was y equal 5 plus 3x. And then it says graph them together. So that's on the following page. And the way to graph this, you don't have to think, well, how do I have to graph a line? What did I learn way back when in some algebra class? If you don't remember, that's okay. You have information right in front of you. You can just use that. So I'm going to use red for the Fresh Plus cost data that we got. And I just want to recognize that I have x values, 1, 2, 3, 4, and 5. And then I have outputs. Those are y values. Those are the costs. So for example, for the Fresh Plus cost, when x was equal to 1, for 1 pound, the y value, the cost was $5. So when I go down to my graph, notice that the horizontal axis stands for x, pounds of meat, and the vertical axis stands for y, which is total cost. So for 1 pound, you can find 1 on the horizontal axis. You need to then follow that up until you get a 5 for how much it cost. So if you look at the vertical axis, you see that it has 0 and then 4 and 8. Maybe think, well, what's halfway between 4 and 8? That's 6. What's halfway between 4 and 6? That's 5. So I'm going to start at my 1 on the horizontal axis and then put a dot that is halfway between the lines that correspond with 4 and 6 for the y value. Okay, so now I need another one. When x was 2 pounds for the Fresh Plus work, we got an output of $9.50. So we can keep organizing our work this way as a way to help us graph. And then maybe think while I'm writing this down, how many points do you need to create a line? You could certainly put all 5 of these on there, but you really only need 2. It only takes 2 points to create a line. So since I don't really have any decimals, I'm going to try to make this easy on myself. I'm going to use when x was 1, I got an output of 5, and when x was 3, I got an output of 14. Those become a little bit easier points to graph. So now I go to where the horizontal value is 3 and up to 14, which is halfway between 12 and 16. And there I get my points. Now I'm just going to connect those with a line. All right, simple enough for that. If you want, you could write the word fresh plus next to that. I'm going to use a different color for my other graph. So now, using green, for the warehouse, when x was equal to 1, the warehouse cost was 8. So I'll go to 1, and I'm going to follow from 1 up to the 8 vertically. That gives me a point. And then I'm also going to use x equals 3 because that gives me another even number. Sometimes easier to use the even numbers. And, oh, look at that. When x is equal to 3 from the warehouse, it's $14 also. Interesting. And then I'll draw a line that connects those two dots. And we just answered the next question. Do the graphs cross? If not, extend the graphs until they do. So we just happened to figure out that they crossed, and you can see that in the graph that I have here. So number 6, the graphs do cross. So then number 7, what is important about the point where the graphs cross? Describe the costs before the graphs cross and after the lines cross. So you can think about it with the graph. You can also think about it with the table. And then maybe just think intuitively. Have you ever thought about something like this before when you go shopping? Do you ever notice that costs are different from one place to the other? Does it start to make sense to buy things a little bit more in bulk at a warehouse store than at just the regular grocery store? Or if you're planning for a big party, do you have to think about those things? So, which store is maybe more expensive for small amounts versus which store is more expensive for larger amounts? Those are some things that we can think about. So number 7, what is important about the points where they cross? So where the graphs cross is, when did it happen? It's when we bought 3 pounds of meat. When we bought 3 pounds at either store. And how much did it cost? $14. Can you look at the graph and see which location is more expensive for amounts of meat that are below 3 pounds? It's the warehouse store, because that graph is above the red line. Whereas after you buy 3 pounds of meat, which one becomes more expensive? The Fresh Plus store. So we can summarize this and say warehouse is more expensive for pounds less than 3. But then it becomes cheaper after that. All right, so you might think, oh, it's not worth it to go to that store unless I'm buying more than 3 pounds of meat. And there you go. That's what we just figured it out. All right, number 8. Under what circumstances would it make financial sense to make the trip to the warehouse store to buy meat? When she buys more than 3 pounds. All right, so what we just did was find a linear function from 2 points. When the graph of a mathematical function is a line we call it a linear function. Notice that line is the root word of the word linear. People put money in different types of investments, like savings account, government bonds, and the stock market. These types of investments have different types of interest depending on the investment terms. One type is called simple interest. Simple interest pays you interest on your principal alone. Note, you do not need to know all the details about interest right now. Just remember that with simple interest, the rate will not change. So suppose you invest a certain amount of money in an account that earns simple interest. At year 2, you have $1,200. At year 6, you have $1,400. We will find the linear function for the account balance after X years. We can find a linear function in 4 steps. The steps for finding a linear function: number 1, decide how to label the explanatory variable and the response variable and choose units for them. Number 2, find the slope. The slope is the rate of change of the response variable per unit change in the explanatory variable. This means how much y changes as x changes by 1 unit. And I want us to remember that. The slope means how much y changes as x changes by 1 unit. We use the letter m for slope. Number 3, find the y-intercept of the response variable. This is the value when the explanatory variable is 0. The y-intercept is also called the initial value. We use the letter b for the y-intercept. So, a couple of phrases: y-intercept is the same thing as the initial value. This happens when the explanatory variable is equal to 0, and we use the letter b to stand for the y-intercept. Number 4, write the formula for the line in the form y equals mx plus b, using the values you found for m and b in steps 2 and 3 above. This formula is our mathematical model. Below, we apply these steps to our simple interest problem. Number 1, we want a function for computing account balance at any time. So we're first going to define our variables. So let's define y as the account balance, and then x is time. In context, it makes sense to measure y in dollars and x in years. It also makes sense that our explanatory variable is time, because we want to think of time as being independent from y, the output, the response. So step 2, we can find the slope by computing the ratio of changes in each variable. So the slope is just the change in the y values, how the account balances change, divided by the change in x values, how the time changes. So, for example, how do the account balances change? Well, they ended up at $1,400 and at year 6, and they started at $1,200 in year 2. So the difference would be 1,400 minus 1,200. So that's what you see in the numerator here, 1,400 minus 1,200. And then the denominator is the change in x. How does the time change? Well, from 6 to 2 years, or I should say, from 2 years to 6 years, that's 4. So the difference would be 6 minus 2 years. So then what we end up with is that's $200 as the change in the account balance, divided by 4 years as the change in the time. 200 divided by 4 is $50 per year. So what is the slope? It is $50 per year. So now continuing on to the next page, step 3. Find the initial value, also known as the y-intercept. We know that m is the slope and b is the y-intercept. Because this is a function, any point on the graph must satisfy this equation. This means we can substitute the coordinates of any point on the line for x and y in the equation, and the equation will be true. We can solve for the y-intercept b if we make such a substitution. So 2 pieces of information are given in the problem. We are told that when x is equal to 2 years, the account balance is y equal to 1,200. So notice what we're about to do. We're going to take the x, which is 2, and we're going to put it in for the x in the equation. We're going to take the y, which is 1200, and we're going to put that in for y. And then we're also going to take the m value that we just found on the previous page, m equal to 50, and we put that in where we see the m. So that means I have 1200 on the left, where the y was, equal to 50 times 2, instead of m times x, plus b. So then our equation becomes 1200 equals 100 plus b. Now, if you're looking at this, you might be thinking, oh no, I got to solve an equation. You could also think, what do you have to add to 100 to get 1200? What do you have to add to 1 to get 12? Has to be 11. So you should get 1100 for this value of b. But to see how you can work with this equation, notice that I can do something to both sides of the equation. I can subtract 100. Why 100? Because the 100 was on the right-hand side of the equation with the b. Okay, so why subtract? What was happening between the 100 and the b? It was addition. So what's the opposite of addition? Subtraction. So that's why we subtract. So then on the left-hand side, 1200 minus 100 gives you 1100. On the right-hand side, 100 plus b minus 100, the 100s just cancel out, and you're left with b. So now we have the slope, 50. We have the y-intercept, 1100. Therefore, the formula for our linear function is, instead of just leaving it as y equal mx plus b, we replace the m with 50, and we replace the b with 1100, and that gives us y equal 50x plus 1100. So now number 9. What is the initial value of the investment? Remember, that's the y-intercept. So that's what we just found for b. That's $1,100. Number 10. The equation found above can give two pieces of information. Data values of the explanatory variable, which represent times, and data values of the response variable, which represent the corresponding account balances. Is the equation a statistical model of these points, or are they part of a mathematical function? Think back to the previous section. What was the difference? For a mathematical function, for any given x value, you're only allowed one response, one y value, which makes sense in this context. For any amount of time, you aren't going to get differing values of account balance. There's only going to be one. That's beneficial for you and also for the bank that you're investing in. So this is a mathematical function. Number 11. Explain what the slope tells us about the investment over time. Go back to what you did on the previous page. Notice what it says right there at the bottom of the page, $50 per year. Is your account increasing? It certainly is. How much is it increasing by? $50 per year. That's it. That's the answer for number 11. The account balance, or the value, is increasing by $50 per year. All right, so a lot of this that we just did is now summarized in the You Need to Know box. So first, be careful to subtract values in the right order when computing slope. The slope formula helps you keep that organized. So if we first call the points x1, y1, so that's my first ordered pair, and x2, y2, that's my second ordered pair. If they are on a line, the slope of that line is then m equal to the change in y divided by the change in x. And you find change by subtraction. So change in y is the same thing as y2 minus y1, And change in x is the same thing as x2 minus x1. Once we have seen the units, we don't need to include them at each step as we did with the dollars and years in the last problem. The units of the slope are always units of y per 1 unit of x. For example, the units in question 11 were dollars per year. So now let's look at a couple of other examples. Number 12. Gary borrowed money from his father. He is repaying his father the same amount each month until the loan is paid off. After 3 months, Gary owes $224. After a total of 7 months, Gary owes $160. Because the loan is being paid at a constant rate, the amount owed, which they are calling y, is a linear function that depends on the number of months x. So amount owed is y and months is x. Part A, find the slope of the linear function. The linear function here gives the amount owed y after x months. So our formula is m equal to y2 minus y1 divided by x2 minus x1. So I need to give some names to some of the information that I was given. So think about it this way. The first bit of information is right after the word after. So it says after 3 months. Remember that x stands for months. So let's call x1, the first x value that I see, 3. And then after 3 months, Gary owes $224. That's the first amount that is owed. So I'm going to call 224 y1. And then in the next sentence, after a total of 7 months, there's another value for months. So that's the second x value that I've seen. So x2 is 7. Gary owes $160. That's the second y value that I've seen. So I'm going to call that y2. Now I have those numbers. So I'm going to put them into my formula. y2 I said was 160. y1 I said was 224. x2 I said was 7. x1 I said was 3. So now I'm going to do my subtraction. All right, so first 160 minus 224. That's negative 64. You can't just ignore the negative. It has to stick around. And then 7 minus 3, that's 4. So negative 64 divided by 4 gives me negative 16. All right? Can we think about what the units are for this slope? What do you think this means? What's going down? What is the negative saying? Well, we're talking about how much he owes. So, how much does he owe? How is that changing every month? Looks like it's going down by $16 per month. So we can say that. Negative $16 per month. That's how his debt is changing. Part B. The equation of a linear function is y equal mx plus b. You know the slope. We just found it. It's negative 16 for this example. Use the slope and one of the points to find the value of b. So how about I use m is equal to negative 16. I'll use the first x value that I found, which is 3, and the first y value that I found, which was 224. I'm going to put those into my formula. So this gives me, instead of y, I have 224. Instead of m, I have negative 16. I have to multiply that by x, which is 3, and then I've got plus b. So now what that looks like is 224 equals negative 16 times 3 is 48 plus b. So it's just like the previous example where I want to get b all by itself. So you could think, all right, I need to do subtraction because I see addition, and I need to subtract the number that I have in front of me, which is negative 48. But subtracting a negative is the same thing as just adding 48. So I'm going to add 48 to both sides. We're still using the ideas of opposite operations. So when I do that, 224 plus 48 gives me 272. So B is equal to 272. So now we put this all together, give the linear function, which gives you the amount owed after X months. So Y is equal to my slope, which we said was negative 16, times X plus my Y-intercept, 272. All right, and then part D. Now let's use our equation. What is the amount owed at 1 year? So how would I solve this? I need to think of what my equation tells me. It tells me for any amount of X, which remember X is months, I will be told an amount that's still owed Y. So they're asking about how much is owed at 1 year. 1 year is the same thing as 12 months. So what is owed? Y equal to negative 16. I have to then multiply that by 12 plus 272. So first, negative 16 times 12 is negative 192. And now add 272, and you end up with 80. So the way to write your answer is, what's the amount owed at 1 year? $80 is owed. It doesn't do any good to go up to somebody and say, Y equals 80. It does make sense if you go up and say, $80 is owed. That makes sense. And then finally, we can find the equation of a linear function by looking at its graph. We just need to identify 2 points. So let's do something similar to the last example, but now we're going to use a graph to get some information from. So first, here's our graph. We see an x-axis that's horizontal at the bottom. We see a y-axis that's vertical on the left. We see some dots that are connected in a line that is diagonal and it's going down and to the right. So number 13, choose 2 points on the line. My recommendation to you here is use some points that it's easy to tell where they're located. So for example, if I go all the way to the right, at the very right of this graph, I see a dot. But can you tell me what y value it has without estimating or guessing? Not so easy. But I'm going to go and find one that is a little bit right of the middle of the graph. And you can see that this dot that I've circled in red, if you follow down, it's got a 5 for its x value. And if you follow left, it's got a 6 for its y value. So I'm going to give that a coordinate of 5 for the x value, comma, 6 for the y value. Is there another point that's easy to find like that? Yeah, maybe closer to the beginning, you can see that there's a point that I've circled in green, and it's got a, if you follow down to the horizontal axis, an x value of 1, and if you follow left to the y-axis, a y value of 7. All right. Number 13 says, use those points and the 4 steps for finding a linear function to find the equation of the line. So let's find our slope first. M. y2 minus y1 divided by x2 minus x1. Go back to the points that you just wrote down, and if you just want to organize this from left to right, 1 comma 7, I can say that 1 is x1 and 7 is y1. And then for 5 comma 6, I can say 5 is x2 and 6 is y2. So this means for my slope, I would have y2, which is 6, minus y1, which is 7, divided by x2, which is 5, minus x1, which is 1. That gives me 6 minus 7, which is negative 1, divided by 5 minus 1, which is So my slope is negative 1/4. If you don't like fractions, we've been using a lot of decimals in this class. Just take negative 1 and divide by 4, and you're going to get negative 0.25. That's perfectly fine to use as your slope. So then we also need to find b. So I'm going to use my equation for a line, and I'm going to replace y with one of the particular y values that I had, which was, let's say with the green y value, 7. And then my slope m is negative 0.25. And let's multiply that by the x value that goes along with the y value of 7, so 1, and then plus b. So this leaves me with 7 is equal to negative 0.25 plus b. So just like in the last problem, how do I get rid of this negative 0.25? Well, I added when I had a negative 48, so I'm going to add because I have a negative 0.25. And I have to also do that to the left-hand side. Now, you can break out a calculator here, but try to think about this. You've got $7 and you add a quarter. How much do you have now? You have $7.25. So that's what b is, 7.25. So now that I know what m is negative 0.25 and b is 7.25, my equation is y is equal to m, or negative 0.25, times x plus b, which is 7.25. So now I've got my equation, and we're going to use it. So number 14, use the equation to predict y when x is equal to 8.5. Very simple. You're just going to take 8.5 and replace it where you see the x, which means to find y, I'll first multiply negative 0.25 times 8.5, and then I'm going to add 7.25. So use your order of operations, negative 0.25 times 8.5 first. That's negative 2.125. And then I need to add 7.25. And I get 5.125. And number 15, use the graph to estimate x if y is equal to 6. All right, so first they say use the graph to do that. All right, so I'm going to go up to my graph. Y is equal to 6. So when I find y equal to 6, I can circle that on the y-axis and then follow that over to my graph. Well, it looks like I can estimate this pretty well. It's when x is equal to 5. We already knew that. Then use the formula to check whether your estimate is correct. What this means is find x when y is equal to 6, which is the opposite of what we just did in number 14. I'm going to take my equation and replace y with 6. So I have 6 equals negative 0.25x plus 7.25. And I want to get x all by itself. And we're going to practice more of those opposite operations. The first thing that I want to do is move anything by addition and subtraction. So I'm going to subtract the 7.25. So 6 minus 7.25 is what I end up with on the left-hand side. That's negative 1.25 equals, and then what I had left over on the right-hand side is just the negative 0.25x. Now take this, I'm going to get a little bit more space with it, and just think, all right, how would I get x all by itself? Using opposite operations. Well, what's happening with negative 0.25 and x? It's multiplication. What's the opposite of multiplication? Division. So I'm going to divide both sides by negative 0.25. So negative 1.25 divided by negative 0.25, and what do you get? 5, which you know has to be the right answer. So we're going to have some more time throughout these lessons practicing steps like this. A lot of the key with these algebraic equations is opposite operations. So the key word for this lesson is opposite.